Welcome back to Fundamental Concepts in Chemical Engineering. Today we're going to be covering a brief overview of introduction of engineering computing skills. By the end of today, you should feel comfortable with the concepts of algorithms, functions, programs, and models, basic operations in Matlab, the idea of conditions and loops, functions, subfunctions, inputs and outputs, as well as basic Excel operations, including constructing functions and performing mathematical operations, plotting, fitting lines, and using the solver app. All right, I'm now going to open up Matlab. Please feel free to join along as appropriate. And a mathematical model can broadly be defined as the formulation or equation sets that express essential features of a physical system in mathematical terms. Essentially, can we write down an equation that's going to predict or describe how a physical system is going to behave? While maybe you don't think about this, we've done this a lot using things in general chemistry like writing down reaction equations, reaction rates. Those are mathematical models. And so we usually want to put mathematical models, express those as some sort of dependent variable, which is a function, so this F symbol, of independent variables, so maybe temperature, pressure, a set of parameters, maybe, for example, the gas constant, and forcing functions which maybe say prevents are additional functions that are going to prevent uncharacteristic or unphysical behavior. So simulations are slightly different than models. So the simulation is the act of running that model or seeing how that model, or the act of seeing how that model is going to, what the result of that model is. So similar, but slightly different concepts. We're going to be implementing our mathematical models in Matlab, which was developed at the University of New Mexico, written in Fortran and improved on in C. There's a bunch of resources available for learning Matlab. You can find these online at mathworks.com. You can go to Google or anything else and say, how do I do whatever in Matlab? And there's tons of resources online to help you with Matlab. Okay, so now that we've talked a little bit about Matlab and functions, I want to show you what Matlab looks like. So now we're in the Matlab setting. So I've opened up Matlab. In this case, it's Matlab 2020. Depending on which version of Matlab you have downloaded and installed, your windows might look a little bit different or appear in different places. You can manipulate that using some of these layout slides right here. But you should see several different things along the top. We have these a home tab. You should see this piece of the window, which sort of shows where we are. So I'm located in my C drive in a folder called Lectures in my CHE 384 folder. This window, this current folders window that I have shown here on the left, is going to show all the files that reside within Lectures. This is just a good way to keep track of what files you have open, what programs you've already written, and then will allow you to maybe call on some of these pre-written functions and files if you want to use their functionality. I also have pulled up the Workspace tab. This Workspace tab is going to show me all of the variables that I've assigned and an overview of what their values are. One of the main windows that we're going to work with is this command window. So it's this space here. So this is essentially the way that I can interactively send variables to and from Matlab. So let's see how this is going to work. So within computing programs, think of it a little bit like algebra. I'm going to take some variable say x, and I'm going to assign it some sort of value, say 5. Right? So in this program that or in terms of MATLAB, I'm essentially carving out a piece of space in computer memory, and I'm telling the computer that anytime I have x within my program or within this window, it should really interpret that x to be a 5. So if I hit enter, MATLAB comes back and it says x equals 5. It's just telling us that that variable x is 5. It shows up in that workspace area on the left where we see x with the value 5. So now I can go into MATLAB and request that it returns whatever piece of information is stored in x. So say, for example, I can type in x, hit enter, and it will pop back out x equals 5. Why is this important or interesting? Well, having x equals 5 isn't necessarily interesting all by itself. The more interesting things are how we can manipulate this material. Because now I can say, for example, y equals x plus 2. In this case, x is an assigned variable, right? MATLAB is going to say, hey, there's a variable here. I should go and look in my memory, in my workspace, right? And look and see what x is equal to. In this case, x is equal to 5. So when I plug it in here, I expect that y should come out to be 7. If I hit enter on my computer screen, that's exactly what will pop out. It will say y equals 7. And all of a sudden, y shows up in my workspace and as a variable, and within that variable is stored the number 7. And I can do any sorts of operations that I want. I could say maybe, what's x divided by y? In this case, I don't have any variable that I'm assigning it to. I'm just essentially using this as a calculator. So when I hit enter, I should see 5, which is x divided by 7, which is y. And I get this number, A and S, for answer. So the answer of my question was 0.7143. So x and y's are my just typical variables that we're used to dealing with in algebra. But I can make any type of variable. I could say maybe x2, instead of equaling 5, maybe x2 equals 1.5. I don't know. When I hit enter, that's now going to store x2, and that's going to show up here. So I can use any combination of letters and numbers, usually wanting to start with a letter, as a variable. So now if I can either say go back and type x2 divided by y, and hit enter. And now I have, it's going to pull this 1.5 to divide by 7, and we end up with this 0.2143. I can do any of the mathematical operations that I'm normally used to doing. So I can say, 2 times 3, 6, using the asterisk. I can do 4 divided by 8, using the slash. I get a half as I expect, and then addition and subtraction, 2 plus 3, 5, 2 minus 3, -1. And I can do all of that with variables or with numbers. So we can just say y minus x. This is a number, -2, because it's 5 minus 7, behaves just like we expect it to. We can do other types of mathematical operations. So say what's 3, we can do it with the variable. So what's x squared, right? So here I can take x, use the caret for an exponential. So move up over 2. So X is 5. If I square it, I should get 25. When I hit enter, this is what I get. Another useful one would be exp. So what's e to x, right? So that's 2.3 something to the 5th power in this case, comes back as 148. Here, I input these parentheses to show that I want to take the exponential of x. I could do, say, the same thing with square root, sqrt of x, and we get the square root of 5. And so within those parentheses are going to say, what submit x to the square root function, and it will do that. Same thing, I can take, say, the natural log of x. Oops. I can take the log of x. We can do when I type in log, it's going to give me the natural log of x. And when I type in log 10, it will give me what we normally think of as log. So that's one little tricky thing about MATLAB. So log is going to be natural log, and log 10 is going to be what we traditionally think is log. Right? So I can do these things with variables, and I can put more complex features in here. So maybe say square root of x plus y. Right? So it's first going to go in here, add x plus y, and then take the square root. So it's gone 5 plus 7 is 12, and taking the square root. If I type in sqrt of 12, I should end up with the exact same number. Right? And so just like before, I could assign these to variables. So I could say a equals square root of x plus y. So now that 3.4641 has been stored in A. What happens if I change x? So this was calculated with x was equal to 5. What happens when x equals 6? So when x equals 6, we can see over in the workspace, we've overwritten that old x equals 5, right? So here we can see that x is now 6. A hasn't changed. If I type in A, I still come back to 3.4641. This is because A was written, or A was stored in memory. The answer of square root x plus y was written when x equaled 5, but x doesn't equal 5 anymore. If I want to go back and change A appropriately, I need to either retype A equals square root x plus y, right? And so now I have the new answer. Or I can use the up arrow key to navigate to a previously entered value, a previously entered formula, and hit enter. Right? And so essentially this is a way we can sort of play in this sandbox and build many different, lots of variables and try out different mathematical functions. Storing all those variables here. But this can be cumbersome, especially if I want to do things over and over again, or if I have a very complicated program. Just finding out what 2 plus 3 isn't very useful. Where this use is going to come in is when I want to build up a series of commands for MATLAB to do for us, and do them over and over again. So what we want to do is we want to build a script or a function. So I'm going to build a new script. So going to new script, and that's going to pop up in what's called an editor. So a script is essentially a series of commands that are going to be done in that exact order. So we can say maybe x equals 5, y equals what do we have? 7. Then a equals the square root of x plus y. So in order to run this, I have to save my very basic computer program. So let's save it. So we can go over to the Save button, click Save As, and we can save it as maybe my first program. When I hit Enter, we should see my first program pop up over in this window. So once it's saved, I can click the Run button. So when I hit Run, we see all the commands that I typed in show up in the command window. We first see that it does this double arrow for input. It says my first program. Then it shows x equals 5. Oh, that's the exact first thing that I put in. Y equals 7. Once again, the first thing that I put in. And a equals 3.46. Right, that's the evaluation for my square root. What we'll also notice is the variables in the workspace have been modified appropriately. So essentially, if I want to write down a whole list of things that I would normally put into the command window, I can put them into a script and it'll run exactly that. Sometimes we don't want to put in we don't want all this information to pop out to the screen. In this case, I've only have 3 commands that are taking place. But as we get to more and more complicated programming, it may be hundreds of variables being written to the screen, which can get very confusing. So MATLAB will let you put in this semicolon. The semicolon means don't print the result to the screen. You'll also have noticed that MATLAB has highlighted the equal sign. This is just done as a way to help you to say, this is going to get printed to the screen. It also, over in this right-hand side, highlights this in orange. Printing things to the screen is relatively slow. Once again, this doesn't matter with such a small program, but when you get to relatively large programs, the actual displaying of these numbers can take a serious amount of time and really slow down your system. So oftentimes we want to hide these. So this time I'm going to change this up a little bit. I'm going to set x equal to 25, just so we get a different number. I can click Save, and then when I'm ready to run, I can either click the Run My Program, or I can type my first program into MATLAB and hit Enter. This time, the code ran. You can tell because over in the workspace, x is now equal to 25, and a is equal to 5.66. So it's changed those variables. However, nothing's been printed to the screen. This is because I've put in these semicolons. So scripts are going to be very useful. They're going to allow us to move information do something over and over again. But sometimes we may say, well, I don't always care that x is 25. So instead of continually going in and changing x equals 25 and writing the script, we can run a program. We can write a function. So here I've just opened a new tab in my editor. And right now it says Untitled 2. So we're going to write a function, and the function is going to take in a variable or more, and it's going to return some sort of variable. And we tell MATLAB that it's a function by writing function. So we type in function, and then we're going to tell MATLAB what it should return. So what do I want out of it? Well, if we're interested in the square root of x plus y, we should probably, if we were interested in that a, which was the square root of x plus y, we can write in a, and it's going to return a. And so maybe we can call this, so then we set equal to, so what is a equal to? This is going to be now a name. We previously called it my first program, but maybe we can call this my first function. Okay, and so when we typed in my first function, we then typed in 2 parentheses to say this is what it's going to take in. You should have seen that when we did that, the highlight on the equal sign went away. That's because it's now recognizing that this is a function. We now need to tell MATLAB that it needs to take in x and y, right? So here we have x and y, and we'll see that x and y are now highlighted, and a is also highlighted with this red underline. These are being highlighted because nothing's done with x or y, and a is also not used, right? So MATLAB just trying to be helpful here. This is okay. We're going to write the little bit of code in a second. The next thing that we want to do is we want to type end. It's essentially a way for MATLAB to know, okay, I can stop, right? This is giving MATLAB essentially its reward. You've completed everything I told you to do. It's time to stop. But now we're ready to write what the function is supposed to do. Now remember, we had said in our script over here, we typed in x equals 25, y equals 7, and then said a equals the square root of x plus y. Here, we don't have to tell MATLAB what x or y is because that's going to be input into this function. So all we need to do is say what a is. So a equals the square root of x plus y. And now here I have a decision to make. I can either put in the semicolon such that it won't print out this line to the screen as the function runs, or I can remove that semicolon and it'll print that line out. I'm just gonna let that ride for a second. So now when I go to save this, it's gonna pop up and it's going to try to save this. It's going to save it as the name, my first function, because that's what the name of the function is. So we can hit save. My first function shows up in that screen and it's ready to run. So how we can run this is we can say my first function, and we can give it different values. So maybe this time 30, comma, 4. When I hit enter, it prints out a, because there was no semicolon here, and it says the answer of that function was 5.831. What you'll notice is this a value in the workspace stayed at 5.66. This is because what happens within the function call does not affect the numbers that are happening outside. Think of it this way. We've written down a bunch of numbers on one piece of paper and a bunch of instructions on a separate piece of paper. We've gone and we've given those instructions and the input numbers to somebody in a different room. So between functions and scripts, we can do a lot of interesting things. So not only can we use the scripts to say, here's a series of protocol or a series of mathematical operations or logical operations to do, but we can actually use them in conjunction with functions. So for example, in my first program, in that script, we can take that x and that y, and we can now put in our function call, my first function. Here we can put in x comma y, and it will save that variable now in a. So let's see what happens when we run the script. So keep your eye on a. So we run the script. Oh, it didn't change because the number was the same. Well, okay. So now I have 25 and 7. I can now change my script to maybe y is 30. Now keep your eye on a. When I hit enter, A now changes because the script that A is written into memory. So the last thing that I want to sort of cover in this, or the second to last thing that I want to cover into this very basic intro is the fact that X and Y are being passed into my first function. But this X and this Y are not the same as this X and this Y. We can see that if we change my first function. So in this case, we're adding them together, so the order doesn't matter. But let's take the case where I subtract one from the other. So because I've made a change in my first function, I need to save that. So here I'm going to say X minus Y. So, and it's going to take that square root. So let's put X is bigger than Y, otherwise we're going to end up with an imaginary number. We can say X is 30, Y is 20. So now when I hit enter, I have the square root of 30 minus 20, or 10. So we can check if A is giving us the square root of 10. Down here in the command window, square root 10. Oh, that's exactly what we expect. So this is going to matter because let's say I swap these. I say Y comma X. When I pass this, when I pass these variables through, it's going to put Y in first, then X. Matlab is going to take that variable that comes in first and assign it to X. Right? So when I run this, I should expect an imaginary number because I should end up with 20 minus 30. And so when I click run the script, that's exactly what happens. I end up with an imaginary number. Even though Y is still less than X in my script, I'm putting in the small number is going in first, then the big number. In essence, right, we're seeing the variables Y and X, but MATLAB is literally writing this as 20 and 30. Okay, so this is a key place that young programmers or new programmers tend to get mixed up is these variables aren't going to get passed back and forth. Good. So as we're writing code, it's going to be very important that we document what our code is doing. This is because we might forget that my first function takes the first variable minus the second variable and does the square root. So we may want to write some things into our codes, whether it's a script or function, that tell us in human readable form what's going to happen. So these are called comments. So to do a comment, we use this percent sign. And so now I can write anything into this comment that I want, and MATLAB will not try to interpret that as a mathematical function. So what would be useful to say is this will take the first number, subtract the second, and take the square root of the difference. Okay, so now when I click go, or when I click run, MATLAB will execute the first line, so it'll store 30 in the variable X. It will store 20 in the variable Y. It'll come down to line 5. It will see these percent signs and move immediately on to number 7, where it will pass X and then Y into my first function and store the result in that A. So when I click go, I'm now back to my positive number because I put in X and Y. and nothing happened with those percent lines. So it can be very helpful when we're writing functions to say, write out in human readable form, this is what I want to happen. And then you can put in the actual code that you're interested in. So here in my first program, we've gotten away with clicking this run. What happens if I try to do that in a function? If I go up here and I click run, I get errors that pop out. So I click run, it says my first function, not enough input arguments. Because when I click go, it's trying to run this, this saved file. But the saved file, that function expects two inputs, x and y. When I click run, there's nothing that actually, we haven't given any input arguments. So MATLAB tells you this by having this red script, which says not enough input arguments. And it even says where the error occurs. Error in my first function, line 3. Right? This error is because it doesn't know what x or y is. Remembering, of course, that the x and y in the workspace are not, what's in the workspace is not passed into the function, right? Essentially, like we've told the person in the next room over, here's the set of instructions, but we never give them the sheet of paper that says, this is x and this is y. Very helpful to write this script, which sort of sets out these inputs and then runs the function. So then you can just click the go in the script and it'll test the function that you're trying to work on, just as a handy dandy debugging issue. Okay, so now, because here if I click run, it will run. Help with debugging by putting in, by clicking on this left side. So here I've put this red dot here, so it will, when I run this next, it will put in x equals 30, x equals 20, but it won't evaluate that. Essentially, it's going to stop the code just to make sure that the first few lines work. And in this case, it's very simple, and it will. So you can see there's this k as this breakpoint here, and we get this green arrow that pops in here that says this is the next line, and I can click this continue button and it'll do the next step, which finishes the program. Or I could have gone in and clicked this quit debugging and it'll just exit out of the entire program. Okay, so now let's go back and put sort of what we've learned into practice. Let's look at a basic chemical engineering problem. For example, let's take a case where we are interested in studying the water-gas shift reaction. If you're unfamiliar with this reaction, it's one of the most critical reactions in the economy. This is where we take carbon monoxide plus water, and we react these, essentially moving the oxygen from the water to the CO to form H2 and CO2. So this is critical in the production of fertilizers, fuels, and will become more important as we continue on towards the hydrogen economy. So let's say we want an easy way to determine the production yield, or how much reactant turns into a product. So how much of that CO and the water turn into H2 and CO2. In the case of the water-gas shift reaction, the chemical equilibrium is highly dependent on the temperature of the system. That temperature dependency of the equilibrium is given by this equation, here, where equilibrium constant is 10 to the power of negative 2.4198 plus 0.0003855 times the temperature in Kelvin plus 2180.6 divided by the temperature once again in Kelvin. So this will give us our equilibrium constant. And if you remember from general chemistry, we can relate the equilibrium constant to our conversion extent for this binary reaction as the following, where the reaction extent is equal to our reaction yield, here's the variable x, over 1 minus x times the quantity 1 minus x. Right, so here's our first model, our mathematical model of the system. So if we were able to solve these equations for x, I could give it any temperature and it would tell me how much my reaction extent was. All I need to know is how to solve this lower equation, which if I multiply it all out and rearrange, we can get a quadratic equation of the form the quantity KEQ minus 1 times x squared minus 2 KEQX plus KEQ equals 0. A nice simple quadratic equation, which we know how to solve via the quadratic equation, where A is this first term, B is the second term, and C is the third term. Right, so let's go in and we're going to implement this in Matlab. So before we implement this in Matlab, we're going to build a scaffold. So just in words, how to solve this problem. Right? So we're going to build a function. So this is what our scaffold is going to look like. So first, we're going to write out what the function is supposed to do, what this code is supposed to do. So we're going to set function inputs, so our temperature, and outputs, and assign the name. Then we need to calculate K. And here I've written out the equation for K. Then we're going to calculate A, B, and C. Right? So those were from the quadratic equation piece. Then we're going to calculate what X is. So X using the quadratic equation. And then we're going to tell the computer to return X to return our yield. Right? So this is 1, 2, 3, sort of 4 operations that we need our model to do in order to figure out how much yield I get for a given temperature. So let's go back to MATLAB and implement this. All right, so we're back in MATLAB. So let's clear out some of our programs. So let me just close out these 2 different programs, and we still have all this stuff left over from last time. So I'm just going to use the CLC command to clear out the command window, and I'm going to use the clear command to clear out the workspace. So as you noticed, the workspace is now empty. My command window is empty. Well, aside from clear, and I can get rid of that. Okay, so let's go in. We're going to build a new function. Going to build a new function, just completely empty. And we're going to take all those words and the scaffolding that we had on the previous from PowerPoint and just put those in as comments so that we can sort of know what our thought process is. So we're going to use that comment key. So, and then we're going to say the first thing that we need to do is set the function inputs t and output x and assign a name. Okay, so then we need to calculate K. Then we need to calculate A. We need to calculate B. We need to calculate C. We need to calculate X, and then return X. So we're going to tackle each of these pieces one by one. Right? So the first thing we need to set the function input and output. So remembering back to how we build functions, so we say function Then comes our output, which is x. We need a name, so let's call this conversion. That's going to be our function name. Now open parentheses to say here's what's going to come in. We have a T for temperature coming in, and we're all set. Now remember, as soon as we put in our function, it's just good practice to come down to the end and hit end. Right, the benefit of that is it's already going to accomplish that last task of returning x for us. Okay, so now we need to do, so we've taken care of the first task. Now we need to do the second task, so in the scaffold, so calculate k. So here we can just type in our equation. So we have k is 10 raised to a power, so we're going to use that caret. And the equation from the previous slide was negative 2.4198 plus 0.0003855 times the temperature plus 2180.6 divided by T, close parentheses. Right? So this is going to operate just like, traditional order of operations. It's going to look first what's in the parentheses. It'll do the multiplications, and then it'll do the additions and the exponential. Okay, so just for our sake, we'll let it output the value to the screen. So we're ready to move on to calculate A. If you remember, we had A is equal to k minus 1. B was equal to negative 2 times k. C equals k. Now, we need to make sure that these are capitalized, because if they're not capitalized, it's going to recognize that as the wrong variable. Okay, so now we're on to that step 11, which was calculate x. So now we need to input the quadratic equation. So x equals, in parentheses, negative b. Now we have an issue because it's plus and minus. But the computer won't do plus and minus. We have to give it one or the other. So what we're going to do is we're going to put in x1, which will be plus, and then we'll do x2, which will be minus, and then we'll compare them. So b plus the square root of b squared minus 4 times a times c. So the key thing here is we can't just say 4ac. We actually have to type in the asterisk for times, or else the code won't know if AC is supposed to be A times C or AC is a variable. So now we're ready to close our parentheses. So when I put in that first one, it shows up and it says, it highlighted that in blue on that first one, just so that you can keep track. One of the biggest places that people make mistakes is parentheses in the wrong spot. Matlab really, as with all computer programs, really takes those matched parentheses seriously. What you'll notice is there's this highlighted parentheses left. And so Matlab is helpful again, saying invalid syntaxes at end of line. This is because we have 2 open parentheses, but only 1 closed parentheses. So we need to essentially close that last parenthesis. So now MATLAB is happy, and we're ready to do divided by 2 times A. Okay, so we can now do the exact same thing. I'm going to just copy paste for x2, changing from plus to minus to account for that other condition. So as of right now, we don't know whether we need the plus or the minus. So for testing purposes, let's just say x equals x1. Right? We can go back in if we were wrong, and we'll test to see whether we need the plus or the minus in a second. So now we've taken care of all the things that the scaffold told us to do. Return x. Well, it's gotten to the end. It has an x value. It's going to put that x back. So we're done. So what we need to do is we need to save the function as conversion. And we're ready to test. So let's type this in. So conversion in the command window. And we can put in any temperature that we want. In this case, let's just see what happens if I put in 500. When I put in 500, we see that a whole bunch of stuff gets spit out onto the command window line. We see that we calculate a K, we have an A, we have we have the calculated B, we have the calculated C, and the calculated X1 and X2. So here's where we still need to use our logic, right? So X, remember, was the amount of conversion. Can I have more conversion than 100%? No. So what I really need is for, so X1 is coming out at more than 100. So, or more than complete conversion. X2 is less than 1, right? So I could have less conversion than total. This is the one that we want. So we want to go in here and change this X1 in our function to be X2. So when I run this again, now my final X, my answer, makes sense. So this is a lot that's being printed to the screen. So I can set it, put in all these, I can put in all of these semicolons so we only get the final answer that we're interested in. So let's save this. We can run it again here in the command window, and it looks great. So now let's see the power of this. So we're going to go into make a new script. So just by clicking that tab. So let's say I'm interested in looking at multiple temperatures. I can say temperature equals 400. And then we can call conversion T. And we could run this once. So when I run it, it's going to ask for a name. So we can call this test conversion. Hit enter. And oops, nothing's going to pop out because I had that semicolon in here. When I run this again, it's going to pop out what that conversion is. But I can do this for many different temperatures. So let's change this. So this is 300, 400. Power of copy and paste. 500, 600, 700, whatever. We can save this, and now when I click run, it's going to execute all of those different commands at the same time running on conversion. And we can see all those popping up right here. Let me clear so we have a nice fresh window. Right? So here I have all those different answers. So far, our class has talked about basic programming, where we take a bunch of mathematical operations and we sort of have this operation. And we have this sort of string of mathematical operations, sometimes only one, and sometimes several operations in a row. And we get to a final answer. There's my horrible handwriting answer, and then we end. But this type of programming very much restricts what we can do, right? I have to go in and I have to know beforehand what I want to do at every single step of the way, right? I need to know step 1, 2, 3, 4, however, all the way down to the end. When you or I do mathematics or engineering problem solving by hand, we have a chance to look at the answer as we go through each step to decide on what the next step should be, right? So think back to our example of looking at the water gas shift reaction, and we had to solve the quadratic equation, right? So we had, we have negative b plus or minus the square root of b squared minus 4ac all over 2a, right? And we had to go in and we had to, by hand, check whether the plus or the minus formula for our quadratic equation was logical. It would be better, and so this is just one example, and it would be better though if our program could go in there and we could tell it beforehand, before we actually run the program, how to make these choices, right? So we would maybe say, want to go in, so make an operation, take the output of that operation, maybe into some choice box. So if I do the plus operation, will I be non-physical? If so, then, pick the negative, or if not, then pick the positive. Then this choice box could lead to different types of mathematical operations that then maybe come back together, maybe not, depending on what we're going to do, and then lead to some sort of answer. In addition to making these sort of split choices, sometimes we may want to go back and redo some sort of operation. Let's say we want to look at something that's going to happen many times over. Well, instead of saying, okay, I'm going to reprogram the same step 50 times, can we put in this back arrow that tells the computer to redo something over and over and over again? So these are sort of the two main ways that we can structure our program. And we're going to go over both of these, first looking at our choice, so if statements, and then going over this going back or loops, and that will sort of round out our structural programming lessons. Let's look first at our decision-making element of structural programming. So the first one, and by far the most used one, is an if statement, right? So this is going to be our general programming tool. So in essence, what we're going to do is say if, let me get my pen. Okay. So if something happens, so say, I don't know, if x is bigger than 0, right? And we can literally write this in. So if a variable x, so here we have our variable, this is our logic operator, and then this is our condition. So if x is bigger than 0, maybe then b is equal to 5. It just sort of coming up with the case, right? So in this case, if x were coming through here, we've done some operations on x. We go through if x, our variable, is bigger than, via our logic operator 0, it will then set b equals 5. Then we need to close that structure just to tell MATLAB, okay, we're done with the if statement, continue on with the rest of the program. We just put in this end, right? And so this tells MATLAB, as it's going through this program, it checks to see if x is bigger than 0. It does this operation if x is bigger than 0, and otherwise it ends.
right? So if x is equal to or less than 0, it wouldn't set b equal to 5. It would just not set b, or it would maintain whatever b was from earlier on in the program. So let's say we want to tell if we want to essentially write our own absolute value program. We could write, use this sort of context to say, if x is less than 0, x equals negative x, end. In this case, right, whatever's happening, if x, because in this case, if x was already bigger than 0, we don't need to do anything, we'll just skip this whole piece. But if x is negative, it's going to enter into this operation that sets x equal to negative x, which essentially turns it into a positive number, and then that ends. So we can do more than just say, if something is satisfies some condition, do something. We can give sets of conditions, right? So we could say, let's say if if a number is bigger than 10, divide by 10, otherwise divide by 2, right? We could either do this through two different if statements, or we can use if-else statements, which are going to work very similarly, right? So we could say, if x is bigger than 10, a equals x divided by 10. And for that or, we write else, a equals maybe x divided by 2, right? And then we can close this by saying end. So let's say, for example, we have x equals 5. The computer is going to take x equals 5. It's going to go through this if statement. It's going to determine if is x bigger than 10? No. So it's going to skip this a equals 10 slide and go down to this else statement. Okay, x wasn't bigger than 10, so now it's going to conduct this next operation, which says a equals x over 2, and then it's just going to continue on with the rest of the program, regardless of what happened in here. And we can string these together by having multiple ifs or nested ifs and these else statements. We can get very complicated and branching programs. So now let's talk about different sort of relationships that we can use. So the first type of example is we want to see if two variables or a variable is equal to a certain number, right? So is something equal? And to do this, we use two equal signs. So it's really critical that we think about this having two equal signs, because if we only use one equal sign, we're assigning the variable. So if we said x1, if x equals 0, it would just reset x to be 0. We need that second equal sign to tell MATLAB that we're doing a comparison. So I'll just make a note. One equal sign sets the variable. Just so you guys have that in your notes. So we'll often find that we, in addition to wanting to see if two things are the same, we may want to see, we want to do something if they're not equal or they're different. So we can use the tilde, that little squiggle that's to the left of the one button on the computer, to say not. So maybe x is not 5. For some reason, 5 is bad, right? If x is not 5, we do a bunch of operations, and if x is 5, then we do something else. Okay? So then we have sort of traditional things: less than, greater than, less than or equal, greater than or equal, just to sort of give you a flavor of these operations. Sometimes we want to look at multiple conditions. We may want to say that we want to maybe do an operation that occurs when x and y are non-zero, or where x or y is non-zero, right? So we can use the ampersand for and, or these double vertical lines, which are just to the right of the bracket sign on your keyboard, to stand for or, right? And in this way, we can string multiple of these logic operators together in to make more and more complex different cases that we may want to look at. So let's take an example and let's write this out. So we want to write an if statement that's going to, we want to look at what, we want to say that z equals x plus y if and only if x is less than 5 and y is greater than 7. So let's write out two logical conditions that will evaluate that z equals y plus x. So we can do this, we can look at the words. So x less than 5, so we can put that in there, x less than 5, and y greater than 7. So essentially just taking these words and putting them into sort of mathematical terms, right? So if x is less than 5 and y is greater than 7, z will be equal to x plus y. Otherwise, otherwise z will be equal to 2. So let's ask a few questions. What's going to happen if x is 3 and y is 8? So first, if x is 3, we're going to go through here and check. The computer is going to go in and check. So when x equals 3, is x less than 5? Yes, great. Then it's going to look on the other side of this ampersand and it's going to say, is y greater than 7? Well, it's 8. So that means that yes, it is, y is bigger than 7. And then it's going to look to see, are both of these conditions true? And it was yes, right? This was yes, they're both yes. So then z is going to be equal to 11. So let me write that in. In that case, z equals 11. So what happens if x is still 3, but y is now 7? So MATLAB is going to go through and do the exact same set of operations that we just talked about. So it's first going to look and see x, which is 3, is 3 less than 5? Yes. Is 7 greater than 7? No. 7 is equal to 7, not greater than 7. So we have one yes and one no. This AND operator means both have to be true, but this on the right-hand side is not true. So this whole if statement is now going to be false. So it's going to say, we're no longer holding true to this statement. So I'm going to go down to this else case, and z is going to then be equal to 2. So we can put z equals 2. So let's look at a slightly different case where we say we want, once again, z equals x plus y, but this case, if x is less than 5 or y is greater than 7. So let's write this in. So we have x, if x is less than 5, now we need our or, so double vertical lines, y greater than 7. Then we can fill in the rest of the information. We'll say that z is equal to x plus y. Otherwise, else z equals 2. And then we say we're done. So what's going to happen if, in the same set of cases, so what happens if x is equal to 3 and y is equal to 8? So first we'll go through. We can think what the computer is going to do. It's first going to say, okay, here I have a 3 in for this. Put this, maybe I'll write in blue. We have 3 in for x. Is 3 less than 5? Yes. Now it'll go over here and check. Is 8 greater than 7? Also yes. If either one of those is true because of or, the statement is true. So then it will tell us that z equals 11. So what's going to happen now if x equals 3 and y equals 7? Maybe I'll pick a different color this time. So if x equals 3 and y now equals 7, I have that 3 is less than 5, so that's true. But once again, I have 7 is not bigger than 7, so I can maybe put like a little check mark. So one's true, one's false. But because it's an or, if one or the other is true, z equals x plus y. Okay, so one of them is true. So in this case, z is still equal to 11. So let's put this into practice. So let's go back to the case that we've been talking about for a while now, the water-gas shift. In practice, the water-gas shift reaction has to be catalyzed. It doesn't happen spontaneously in the gas phase. Additionally, when the temperature of the reaction is less than 600 K, the conversion falls off very rapidly as the catalyst becomes inactive. We can model that catalyst becoming inactive using this equation. The true conversion is the thermodynamic conversion times this expression that takes into account catalytic deactivation. Okay, so in essence, we need to split our code up into two pieces. So before, right, we had input, which brought in maybe the temperature. We calculated K. We calculated A, B, and C. And then we use the quadratic formula to calculate x, or in this case, x naught. But now we need something that's going to take x naught and determine and branch it into two pieces. One where the temperature is less than 600, and one that's greater than or equal to 600. In the case of less than 600, we need to put in calculate x from x0. And in the case that we're greater than 600, we just set x is equal to x0 and then end. Right? So let's go in and put this a little bit into that scaffold form that we just looked at. So right, so in building this code, we need inputs. For right now, let's just take in t and output x. Then 2 will calculate k. 3, I'm going to just shorthand this as to calc. To calculate x naught. 4, we need some sort of if statement for x less than 600. And then 5, return x. All right, so this is sort of our scaffold. So we can now take this idea, this written out set of instructions, and put them into mathematical terms in MATLAB. So I'll see you over in MATLAB. So now that we're back in MATLAB, we can come in and take sort of our old conversion code and modify it to take in this if statement. So first I'm going to modify this by naming it a different something different so that we don't accidentally overwrite our working code. So here I've just called this cat underscore conversion, which is going to take in t, and then we go through our normal calculation of k, a, b, c, and then calculate our different x's. So this is that first bit of the scaffold. So I'm going to now just put in the new piece that we need. So we now need a piece that's going to determine if t is less than 600, and if so, implement that catalytic conversion equation. Implement conversion. Everything else is essentially the same. So I'm going to go through here because if you remember back, x was what we were returning. So I'm going to change this x here to be x0, right? Because we want to have that variable to play with. So now, in order to implement this check, we need to write our if statement. So if, and then the very first thing that I recommend doing after you type in if is hit enter to type in n, just so you don't forget to put that in there. Okay, so now we need to know if temperature is less than 600, right? So I have my variable that I'm going to check, t, the operator less than, and 600. Now I'm going to implement my equation, x equals x naught times exp negative 50,000 divided by 8.314 times t plus 10. All right, so just copying and pasting or just typing out that equation, and that will give us our conversion. We'll just make it quiet by putting in that semicolon. So we can either leave this here, but right now, in case the temperature is bigger than 600, we have no x. So we probably want to put in an else statement that says if it's not less than, we want x to be x naught, right? Just to round that out. Okay, so this is as easy easy peasy piece of cake. So let's check and see how this goes. So let's take t equals 700, and we'll throw it in here. So cat conversion t. All right, we have a number, and now we can put in something that's less than 600. So say t equals 550. We can go in, put that into cat conversion again, and now we have this number that's, now we get an answer. If you remember back from our previous code, when we previously put in 500, before we took into account the catalysis or that if statement, and we got this number that was much bigger than the current number that we get when we take into account that conversion, which means that our if statement was working. So we have our conversion. We can check. We know that our if statement is working. So let's see what happens when we try to put in our, just like we did before, we can go say from 300 in increments of 50 up to 700. This should mean that we have some portion of the code going through this, executing this first piece of the if statement, and then the other 2 or 3 points going through this else statement. So let's see what's going to happen when I click, when I input this new temperature into the cat conversion code. So when I do this, scroll up, what we see is that my 300 degrees C, 350, 400, all the way up, doesn't look like it's going through that first if statement. Why is that? That's because MATLAB doesn't know how to deal with this if statement, because if t is an array. So it's going to look for any case where one of my values satisfies, or it's just going to sort of skip that, because it doesn't know how to evaluate a whole array being compared to 600. So when we put a series of these values, so this range of temperatures through this if statement, that if statement is going to default to the else. So we need something new that's going to help us walk through all of our different t's in order to walk through all the different t's if we want to look at multiple t's at the same time. And so this is where loops are going to come in handy. So what we really want to do is we want to loop over every single t and evaluate that if statement. So, and this is just one case of where loops might come in handy. So when we're looking at loops, we can think of 2 different types of loops: for loops and while loops. And let's take a second to talk about these 2 types of loops, and then we'll go back to MATLAB and see how we can adjust the code to take these loops into account. So the first type of loop is a for loop, and so this is going to be when we know how many times we want to do a specific task, right? So we've put in there, we have some sort of data set, and we want to do something, say 10 times, and we know from the beginning that that number is set. So in the case, sort of in the water gas shift case, right, we know that we want to do that check to see if we're less than 600 degrees a certain number of times. That number of times is the number of elements in the array, right? But it's preset at the beginning of the code. We know how many times we need to do that. The other type of variable that we need to consider are while loops. It's sort of like a for loop, but this is for cases where we want to do an operation until something happens. Or in another way, when we don't know how many times we want to do a certain operation. So let's go and look at each of these types of loops, then we can decide what we want to do in our water gas shift code. So here's an example of our for loop. So in our for loop, it's going to contain a similar set up to if statements. So we're going to call first on for, but we're going to set a new variable. So this I is going to be a counter, and it's going to count. And it's going to count from A. So we'll call this begin. So it's going to begin with I equals A. And then every time it goes through the loop, it's going to increment by B. And it's going to end when I is greater than n. Okay, so all of this information is set up in this single line. So we set up a new variable that's going to act as a counter. We tell it where to start counting. We tell it how much to increment the count by, and then we tell it when to end. After we give it all this for loop information, we then say what types of operations we want to conduct. Okay, what are the mathematical things that we want to look at? And then of course we have our end statement to tell MATLAB stop. So when MATLAB gets to end, it's going to go back up to the for loop, do that increment, go through the operations, and it'll keep looping here. Let's look at an example. So the easiest or most straightforward example could be the case of a factorial, right? So if you don't remember, 3 factorial is equal to 3 times 2 times 1. Oops. 3 times 2 times 1. So a factorial, we take the number and then multiply by 1 less of everything. Right, so if we were going to write this, we need a for loop because we know how many times we want to do something, right? So in the case of 3, I want to multiply 3 times 2 times 1. So I want to run this loop of multiplication n times, right? Whatever this sort of 3 is. Okay, so we can start off with saying x equals 1, and then comes our for loop. So we start our counter. So in this case, I, and usually for loops, we try to pick I just so that we know that it's a for loop or while loop. We set I equals to 1. Right, and so then we're going to say x equals x times I. Then it's going to hit this end, it's going to come back around, it's going to then increment by 1, right? If I don't have a b, it just assumes b is 1. So then it'll go to 2. So then it'll say x equals x times 2. Then it'll come down to the end, loop around. In this case, it'll increment by 1. So then I will be 3. So then x equals x times 3, end. And so we're going to loop through here again and again and again. So so on the first loop through, so first time through, x equals 1. The second time, oops, maybe let me write this out this way. First time I equals 1, therefore x equals 1. The second time I is equal to 2, x times x, which is 1, times I, which is 2, is 2. Then we go through for the third loop, we get to the end, we go back, I equals 3 this time. So then we come in, x equals x, which is now 2, times I, which is now 3, so x equals 6, which is 3 factorial. And we could do this again, we could go to 4, I is 4, then this becomes 24, and so on and so forth. All right? So these are for loops. We know how many times I want to do something. So let's do this modification to our code. So here, instead of saying I want to multiply every time through, I want to take every variable in T and run the sets of operations. So we need to code all the way back from the beginning. So we need our input and output. So this would be t in going to x out. Now, because t is going to be t is going to be changing, or we're going to add that modification at the end, we get to keep our k, so we can keep those outside of the loop, right? Because the pre-exponential isn't going to change. Or sorry, the equilibrium constant isn't going to change, so we can just keep calc k. I'm going to wrap these all together again, so calc x0, but now I need my for loop. So we need a for loop, so we want to loop over the index of t. So we hit every single one, and then within here, I'll maybe call this A, check if t is less than 600. And if it is, put a Roman numeral, then calc the catalyst piece, right? So essentially we get to keep a lot of our old code. So we get to keep a lot of this code, but we need to add in this new looping over our index pieces. So let's go over to Matlab. We can bring in this new idea of the loop and implement it. Okay, so let's add this piece in. So if you remember from our scaffold, we need the loop to be before, we need to loop over the t's, the temperatures, before we get into this if statement. So we need to put this on the outside, so loop over indices. So, right, so we know it's a loop, we have a for, and now we want to put in our end, and we want that end to be after that if statement. So we can put in this end, and MATLAB will handily, if you click on end, it'll highlight the for, and if you click on the for, it'll highlight that end, just so you can see what's going on. So now we want to look at every single index in T. So we can say I equals 1, because MATLAB starts with 1, colon, we're going to increment by 1, to however long t is. If you remember back to the first discussion, or I guess the discussion from Tuesday, we can use the length command on t, and that will allow us to count from 1 to however long t is. Right? Okay, so now this is going to loop us over our indices. Now here's the problem. It still doesn't know which t to look at. So I'm going to include in t the index I. Right? So I'm going to look at the ith index to check in this expression. What we need to do, of course, now is put in the indices for everywhere that we have a variable that's going to change. So we have some ith instance of x0, we have an ith index of t, we have an ith index of x. I think that's all of it. And then we have the else statements, I naught, x naught, there we go. So now we have all of these indices. Right, so I is going to change by 1, it's going to look, it's going to take in an individual t and evaluate this if statement. You can already start seeing why it's helpful to put in these indents. So I'm going to input an indent here. So now it's very easy to see that this for loop matches with this n, and everything else is going to happen inside. Right? So we can see what's sort of held within each subcommand. Now, let's try that cat conversion code with our set of t's again. So when we do this, we see that now instead of monotonically increasing as temperature decreases, we have this sort of 0, which increases, and then starts decreasing. So just to see this on a plot, we could plot t against the answer, and we should see this figure pop up where we can see now we have this increase in activity and then decrease in activity. Okay, so hopefully you can now sort of see how we can use for loops, where for loops are going to come in. Very handy for moving through indices and things like factorials. So let's go back and talk about while loops. So while loops are for cases where operations are going to be done over and over again, but we don't really know how many times we want to do it. In the water gas shift example, we knew that we wanted to do it, we knew that we wanted to do the operation for however long t was. But there could be a case where we don't really know what we're looking for. So a while loop is going to do a task again and again until some sort of condition is reached. So in this case, we're going to have some sort of variable, and we're not going to set that variable, right? So in a for loop, we said I equals some number to some other number. Here we just say while a variable, or as long as a variable I, meets some sort of logical condition in relationship to some comparison, then we want to do an operation. So let's look at an example. So let's say we want to count how many times it takes to go from n to 0 in increments of dn. Right? So here we don't know how many times, how many times a dn goes into n. We want to figure that out. Oops, sorry. So we don't know that a priori or beforehand. So we're going to need to use a while loop rather than a for loop. So in this case, I can set a variable steps that's going to set to count how many times it takes me to decrease to 0. And then I have my while loop. So n is coming in from the beginning. As long as n is bigger than 0, I'm going to do these sets of operations. So let's set up this sort of table. So we'll call it step 1, 2, 3, 4. We don't know quite how many of these steps are going to be needed. And we'll say n. And we can have steps. And let's just say that we're going to call this with n equals 5 and dn equals 2. Okay, so what's going to happen as I go through this series? When I first start, steps is 0. I'm going to come to my while piece. It's going to say, what is n? Well, in this case, n is 5. Is 5 bigger than 0? Yes. So my new n is going to be n equal to n minus dn. So 5 minus 2 is 3. And steps is equal to steps plus 1. Well, steps was 0, but now it's 1. It hits the end, and then it goes back up to the while piece, right? It just kicks it back to this while. So now it goes in and says, is n bigger than 0? Well, in this case, n is 3. 3 is bigger than 0. So it's going to say n is equal to 3 minus 2. Oh, that's 1. Steps equals steps plus 1. That's 2. It comes to the end. We go back up to the top. N is now equal to 1. Okay, is 1 bigger than 0? Yes. N equals n minus n1. Ooh, let me pick maybe a different color for this next round, maybe orange. So I now take n minus 1. That's negative 1. I don't stop then because I haven't hit end yet. So I do steps equals steps plus 1. I get to 3. Right, because 2 plus 1 is 3. I now hit the end. I go back up to while. Now I have n is negative 1. Is negative 1 bigger than 0? No. So I get to go through and I leave that while loop. But since I left that while loop before I got to increment, before I did any of those other operations, steps is still equal to 3. And that would be what would show up if I accessed steps outside of the loop, or when I get to that end, that 3 is what's reported as that final value. Okay. So now that we've covered the basics of loops, I want to talk about nesting. So nesting is what happens when we want to loop over multiple variables. So I can do this with for loops or while loops, combinations of for loops and while loops, and in conjunction with if loops. And these three things are what makes coding so powerful. So nested set of loops is when I loop over one variable. Let's say I have this matrix A. I have one for loop indexed with I that's going to loop over rows 1 through 3, and then I'm going to loop over J, which is going to loop over the columns. Now I know that I is going to interact with the rows because I is first, and J is then going to index over the columns because J is coming up second. So let's very quickly talk through how this is going to start. So step 1 is going to set I equal to 1. Then when I go down to step 2, J equals 1. So when I come down to step 3, Aij is going to be equivalent to A11, which equals 1 if I go back and look at that top column. So then it goes through to this if Aij is equal to 9, it's 1, so we don't. We come down to this end. When I'm done with this end, it's going to go into the next step to this end. This is going to come all the way up here to this J. So let me switch colors really quickly. We'll go to purple. So then the next step 3 is going to set J equal to 2. I is still 1. So when I come down to the next step and I say AI comma J, what I'm talking about is A1 comma 2. In this case, it's equal to 2. right? And so I can go through this to step 4, where j is equal to 3. I get ai comma j equal to a1 comma 3. So then this equals 3. So once j is 3, I come through to this for loop. I complete that for loop and I hit this end. And now I'm ready to move on to this next step, so this next end. When this has now been hit, I come back all the way up here. So I'm ready for number 5. In this case, I is going to increment by 1. So all of a sudden, I is now equal to 2. So I go down to this next step, back to my j. Now I'm starting j all anew. So j equals 1. When I go on to the next line, I end up with ai comma j equal to a2 comma 1, which should be 4. And this will increment over the j's rapidly and over the i's slowly. So by doing these nests, I can access all 9 pieces of information in that A matrix and do whatever manipulation I want to on that A matrix. Great.
All right, now that we've covered basic programming through MATLAB, I'd like to show you Microsoft Excel. This is another program that we use extensively in engineering and chemical engineering. Yours might look a little differently depending on which version of Excel you're using, and then whether you're on Windows or a Mac PC, but these should all be here. First, a sort of overview, we have this giant set of cells, which are labeled going across in column order with numbers and down in the rows as, I'm sorry, across in columns as letters and down rows as numbers. We have, of course, files where we can do any sort of saving, and we'll get into some of the other insert things later. All right, so one of the first things that we might want to do is input various data. So let's go through, we can have some sort of independent variable x and some sort of dependent variable y. And we can say we're interested in looking at x, I could type in 0, type in 1, type in 2, type in 3, etc. And then I, of course, can have some sort of y's that might go with that. So let's maybe say 0, 1, 4, 9, right? So this would be representing a parabola. Okay, so I can just input numbers. I can input text, right? So I could make a note to myself, this is a parabola, or I could, put in a function. So let's maybe have some sort of new, y calculated. So in order, I can have essentially Excel do math for me, right? If I type in the equal sign in the box, I could then type in a formula. So let's say I wanted to have x squared, right? So I can take x, I can click on that button, right? And by clicking on that cell, it will autofill B4, or I can go in and I can just type in B4 and it will then give me that cell. Now to make the parabola, I square it, sorry, so I use the caret sign and then a 2, and then that's, when I hit enter, it will fill out that equation. I can either then go in and repeat filling this in down, or I can go over to the lower right hand corner. I should see this, my cursor change to being a different shaped cross. If I click, I can drag down and it will then use that same equation in all of these boxes. Okay, in a lot of times in chemical engineering, we'll have something that might change in terms of temperature, right? So maybe I have a reaction exponential, a reaction constant, right? So I have K, and remember that's our K, that reaction rate constant is equal to A exp minus EA over RT, right? So I could go in and I could say, okay, I know what A is, I know what EA is, I know what R is, and I want to see how K is going to change as a function of temperature. So let me say temperature, I can have K, and then I can go in here and say maybe this is um, equals to 5 times 10 to the 13th times per second. Maybe the activation energy is 80,000 kilojoules uh, per mole K, and then R in that appropriate unit is 8.314 joules per mole K. Okay, so I've got my these sets here. Let's just start out at say 300 Kelvin. I can now build an equation using that sort of equal sign like I've shown before, and we can use that. So previously we had gone in, I could say, okay, I need A times, whoops, times exp, right? So that's our exponential function, -1 times EA divided by R times T. Now, it's very important to make sure that you're using the parentheses in the appropriate places, or else it's not going to give the um, correct expression. Excel is going to help you out here by sort of color coding this, so right, we see, A show up in blue, so we can correlate that here. This EA is showing up in red, and then I've got purple and green just to sort of guide the eye. Okay, I hit enter, so then this gives me, my rate, which would be in this case, 1 per second. And so then let's see what happens if I go to do this again at 350. I could do the same trick where I pull this down, and all of a sudden I get this div by 0. That's because when I pull the formula down, it's not only going down this row, I'm looking at, pulling from B17, but it's now pulling from C14, E14, and G14. That's not what I want. I still want it to pull from these cells up here. So I can move them up, but I don't want to have to do this over and over again. So what I can do is I can use the dollar sign symbol, which will fix the cell that it's referring to, right? So I can add in a C $13, E $13G uh, $13, and then I want to leave B17 without a dollar sign so that when I pull down, it's going to pull that appropriate sets. Okay, so now that I fixed that, I have a number. I can now go in and I can look and see what happens at 400. When I pull this down, I now am pulling from only these values and to the left. Okay, so I can do this. I can have a few tricks. So Excel tries to help you out. So it sees that I'm adding 50 each time. So if I just take those numbers, even though they're input as numbers instead of formula, pull it down, it tries to guess. And sometimes it works and sometimes it doesn't. But simple additions tend to go pretty quick. It's pretty good at. All right, so now I have this table. I can of course go in. I could change the activation barrier. I could say maybe make that 90,000. And when I enter that, Excel will automatically update all of the cells in that function. Okay, so then the other thing that I can do that I want to do a lot is make a graph. So there's several different ways to do this. So I can go to Insert, and then Insert, I see a whole bunch of different types of things. Here I want to insert charts. For right now, we're going to put in a two-dimensional line plot. I, of course, could do Scatter plot is also used a lot. Sorry. So scatter plot and line plots are probably two of the most prevalent ones used in engineering. Um, in this case, Excel is actually sort of guessing which data I want to put in there, and I can put in these graphs. Okay, if I want to change or add data, I right click on the graph itself. I can then click Add Data. I go to this Add button. I click on the X value. I can then drag down to get my X's. I can then drag down to get my Y's. Hit Enter. OK. And then I'll see, in this case, uh, nothing very much because I've got two things saying the same thing. But I'll show you in a second how we can make that different. So let's say we have a sort of a K2 that's going to use a different EA. Let's make this one 100,000. I can grab this and drag to the right just like I did before. Of course, we're going to have issues because it's pulling from the wrong location. So I can correct these. And what this is just doing is showing you that you can sort of drag things to the right and it's going to move. Assume that the formula is going to pull from the right, but I can now do that, and by double clicking, um, whoops, sorry, let me do this a different way. Let me drag this to the right, put these all in the same cell. Backdrop, there we go. Instead of dragging down, I can double click and it'll autofill. Okay, so I can drag this over and we should be able to see now I have two plots. I have the blue, which represents K1, and I've got the orange, which represents K2. I now want to show us how I now want to show you how we can do data inputs and line fitting. So to do this, I'm going to go to a new sheet. So if I go down to the bottom, I should see sheet 1. So this is just the workbook that I'm working in. I have sheet 2. That's going to give me a clean set, or I can, of course, click this button and get a brand new sheet. If I want to rename these, I can right click on the button. I can click rename and say, fitting lines. Okay, so what we're going to do here, I'm again going to have X, Y, X and Y. We'll do, say, 0. Then let's take this and we'll add 0.25. I can drag this down, and I've got a bunch of different points for Y. Let's say let's have M and a B that we'll use. Maybe M can be 2 and B can be -3. I can say Y equals M, and I don't want that to get dragged down, so I add that. So M times X plus B. And that B, of course, I need my $sign. And then I can drag this down. Okay, so I can highlight this, go to Insert, look at Graphs. I'm going to add in a scatter plot, and I have my scatter plot shown here. And then just for fun, I'm going to add in a little bit of random information just so, just so it's not like a perfect graph. Now that I have my randomly generated data, we can see my randomly dispersed data. We can see that we sort of fit a line in here. And this is going to be how data is going to come in engineering. It's not going to be nice and beautiful and perfect. Okay, so let's see how we can fit this. So if I click If I click on the data set, it'll highlight it. I can then right click and do this, use this feature called Add Trend Line. It'll open up this panel to the right where I can have different types of fitting functions. So for example, a linear line, right? That's what we expect to see. If it'll show us this dashed line, hey, it fits pretty well. If I click this button, display equation on chart, it will show what the line fit equation is. And then of course I can add in, get some statistics, including, what the R squared value is. So the fit here is 0.977. It's a pretty good fit because I took the correct sets, right? I have, you know, a really good fit for the slope, and then that intercept is okay. Yeah. Cool. And I can do this not only for a linear fit, but I could have, say, tried to fit a polynomial. So this would be a second order polynomial. Um, I have an x squared. I can change the order of that polynomial to be, a cube set, et cetera, et cetera. Okay. And so from this, you can get most of the line fitting and extract information. The last thing that I want to show you is inputting data. So let me show you a set of data that I've constructed here. So let's say I've gone to I've gone to the lab and I've collected this data set, whatever that means. And I've exported this data from my instrument. How can I put this into Excel? Well, I have this data. I'm going to copy it and then go back into Excel. Okay, I'm going to start in a new sheet. If I go and I click paste, I have this data, but it's not, each data point isn't in its own cell. You'll notice that cell 3B contains the entire first line. This isn't very useful. I need to do something with it. Okay. So what I want to do is I want to grab all of the data, all the information, and then I need to do what's called uh, text to columns. So if I go up to the top, there should be this tab that says data. It might be in a slightly different location, but for you, but in data or somewhere, you should see this set that says text to columns. When I click that, it will take me through how I want to convert that text into numbers. And so the most commonly used one is going to be delimited. And so we'll stick with that for right now. So within delimited, I have several different options. In this case, each data point is separated by a comma. So I want to make sure to click the comma button. When I do that, you'll see that these lines have now shown up. If I click finish, I now have all of this information here. Okay, very good. The last thing that I want to show you, and so then I could do that if I had tab delimited or semicolon delimited data. However I want to do that, I can pull that out there. Okay, so another feature that we have in data, which is very useful, is called sorting. I can sort largest to smallest. And when I do that, I can either have it expand the section. So, it'll move all the rows together or just the current section. So if I expand the section, I now have all the data that goes from smallest to largest, and it keeps everything together. Okay, so Excel also has a bunch of inbuilt features. I could take the average, and I can do that by typing an average, highlighting the data I want to take the average of. Here in this case, it's 0.35. I can take the standard deviation, again, highlighting uh, those columns, enter, and I'll have my standard deviations. There's many other functions that are practical, including min, max, median. So all these sort of functions that come up over and over again. All right, lastly, I want to show you a thing called solver. And we're going to do a very, very simple case. Let's say that I want to know, um, I have some sort of function, x and y, and maybe y is equal to, um, oh, sine of x times exp to the negative x, for example, right? And I can go in here 0 point, could do 0, and then u plus 0.1, and then of course drag this down, and then we can look at a graph. Okay, and so let's say I wanted to know where this function, what the value of x is. Let me write this out. What is x such that y is, say, 0.25, right? So I can do this using the solver routine. So what I do is I can say, okay, hey, what am I looking for? I'm looking for, so I'm going to move this here just a second. I'm going to say, okay, hey, I want y to be 0.25, so I'm going to take whatever this y is, subtract off 0.25, and I'm going to go to this data solver button. I'm going to set my objective. I'm going to search for this set. I'm going to do this and say that I want it to be equal to 0, but I could, of course, say maximize or minimize it by changing this value of x. Okay, and when I click run, it'll give me a value. Okay, this one didn't do a very good job, but we're close. Sorry, I want it to be 0.025, not 0.25. Okay, let's try that again. So let's go in here. We're going to click the solver. We're going to set that to 0 by changing those values. And then I go through and I get my solution. And that happens at 1.364, or y equals 0.25, exactly what we were looking for. Okay, and with that, that's a very brief introduction to Excel. There are many more videos out there that will cover Excel in great detail. This is a very powerful software that you can use, but I think this sets you up for everything that you will need to know moving forward. All right, well, that's going to conclude our review of Intro to Engineering Computing. I know it was a whirlwind, but hopefully you now have the basic concepts of how you can use both MATLAB and Excel to do things like executing functions, plotting, line fitting, solving for things, thinking about conditions and loops and inputs and outputs. All right, remember to take the quiz, and I'll see you next time.